This lesson we are going to study applications of complex numbers in adding sinusoids with phase difference. Well, if it's too much to know or think about, let us break this down into topics from what you know to what you don't know. So let's start with the term sinusoids. Sinusoids are nothing but graphs of the sine and cosine function. If you have never seen the graph before, let me tell you, sin x is defined as the ratio of the opposite side in a right triangle to the hypotenuse. And as the angle changes, the value of sine also changes. And I am showing you the graph of sin x between minus 2 pi radians to plus 2 pi radians. What I would want you to know, that is prior knowledge, is that after 360 degrees, the graph repeats the values after 2 pi radians or 360 degrees. Therefore, you see between minus 2 pi to 2 pi, you see two cycles of completion of the sine graph. So say for example, it starts from 0, it goes to the peak value at pi by 2, comes back to the 0 or average point at pi, goes to the minima point and then completes the cycle at 2 pi radians. Okay. Similarly, this cycle also starts from minus 2 pi, goes to the maximum at minus 3 pi by 2, comes to the average, goes to the minima, comes to 0 and repeats. So that's how a sine graph behaves, and cos similarly. We will look at the cos graph later, but this is how the sine graph is. Now there are two things that we have to know about sine graph. One is frequency with which it repeats, and one is phase difference. These are the two things that I'm going to show you in this graph. So let me show you a graph, same sine graph with a higher frequency. So if you compare the black graph and the purple graph in terms of their equation, one of them is sin x, another is sin 2x. So the number that multiplies with x is indicating the frequency. So it's double the frequency of sin x, which means frequency is the number of cycles per unit time. So if it's double, that means sin 2x should have 4 cycles completed within that time frame. Is that true? Let's see. So I start with minus 2 pi, go to the maxima, come to 0, come to minima, come back one cycle, go to maxima, come back second cycle, go to maxima, go to 0, go to minima, come back third cycle, and yes, this is the completion of 4 cycles. Absolutely yes. So the purple graph and blue graph, black graph are same in terms of amplitude, are starting at the same point, but they are working with different frequency. An example of frequency could be that there are two phenomena in business, like an inventory cycle, one which is periodic quarterly and something which is periodic half yearly. Then the frequency for repetition is changing, correct? Similarly in physics, I could have two musical instruments with notes of different frequencies. So higher frequency in physics can be sensed as pitch, higher pitch, and that's something that you can understand frequency as. Now that is one thing. So two signals, two sinusoids or two functions can change in frequency, but that's not what we use complex numbers for. We use complex numbers when there are sinusoids with a phase difference. And what does that mean? If you look at the red and the purple graph in terms of the equation, one of them is sin x and another is sin x plus pi by 2. So something has changed in the input. The frequency has not changed because x is multiplied still with 1, but it is like shifted. If you see the red graph and the purple graph, let me show you the corresponding points. Okay, look at the minima points. It seems the value is the same, but it seems it occurs at different times, right? Look at the maxima also here. Look at the corresponding points. The value of maximum is same, 1, but they are occurring at different times. One of them is occurring at 0, another is at pi by 2. So therefore they are shifted with respect to each other, and that's one of the ways to understand phase difference. So let me show you another example. Here again, look at the black graph and the blue graph and the purple graph. Again, if you compare the corresponding points, do you see how they are shifted with respect to each other? So that's what we mean by phase difference. They occur at different times. Can I have some examples from business or economics which do similarly? Yes. So there can be seasonal consumptions, that means they happen at the same frequency. So there can be an yearly frequency for ice cream or winter clothing. They fluctuate seasonally. But these fluctuations and these fluctuations, whatever is fluctuating seasonally, which means is repeating, can be modeled using sinusoids. But they could have a phase difference which represents the time lag between the peak demand. So we just saw how the graphs were having different times at which their peaks occur. Could that be a possibility for ice cream demand and winter clothing demand? And what about economic activities tending to follow cyclical patterns? Well, different economic indicators may fluctuate with different timings. So the phase can be an indicator of the sequence in which they occur in the business cycle. Correct? There can be some lagging factors due to changes in the overall economy, like unemployment rate, or it could be leading to other things like a recession or a fall in the rental values or in the real estate prices and so on. So these are some examples where the start time or the time at which their peaks occur, if they are different, then we have sinusoids with a difference in their phase. And that's what we are going to study with in this unit or in this subtopic on how do I use complex numbers to add sinusoids. So let me represent, and please don't worry, you have a calculator. Remember, you will not be doing anything, any calculations manually. So all you have to do is look at putting these numbers in the calculator. So the first question I'm looking at is, I have two sinusoids, and sinusoids means I can have a cos function or a sine function. Okay, if you want to see how a cos function looks like with respect to a sine, so instead of a sine function, I can graph a cos function for you. That's a cos, and I can have a cos with a phase difference. Okay, so these are two cos functions with a phase difference. The time at which their maxima occurs is different, so they are shifted with respect to each other. So I'm looking at a cos function 4 cos x. Okay, the frequency is the number that is multiplying with x, and the other function is g of x, which is 3 times cos of x plus pi by 4. So if you see, the amplitude is different. Amplitude here is 4, the amplitude here is 3. The frequency is same because the number that is multiplying with x is 1 in both cases. And what else is different? There is a phase difference because of this pi by 4. Let me also show you how does addition with different frequencies looks like. So if I have the two signals with different frequencies, if they are added, what happens? It results in, this is not a sinusoid. This is a combination of sinusoids with different frequencies. Look at the graph. This is no longer a sinusoid. But what are we looking at? We are looking at adding sinusoids with a phase difference. See, look at here. For example, sin x and sine of x plus pi by 2 was added. It results in the in a sinusoid of the same frequency. Can I compare the original graph and this? Look at it. Same frequency, but of course the phase will be different and the amplitude is different. Frequency is the same. The time at which the peaks occur is different, and the amplitude is also different because I'm adding two signals. Obviously the amplitude will be higher. That is what happens in this case. So which is why it is important that we will be dealing with only signals with same frequency and having phase difference alone. So what do I do? So I know that e raised to ix, instead of theta I'm writing x, is equal to cos of x plus I sine x. That's what I learnt when I discussed the Euler's form of representation, isn't it? R is 1 here. Okay. So I can write f of x as the real part of 4 times e raised to ix. So why for real part? Because it has only cos x. And what can I write g of x as? g of x is the real part of 3 times e raised to I x plus pi by 4. So both the number, the original sinusoids, have been represented now using complex numbers. What do I want? I wanted to add f of x plus g of x. So can I say, after adding the two, if I take, after adding these two complex numbers, all I am interested in is only the real part of the sum, because what f of x and g of x were only real parts of the complex number. So after addition, only take the real part. That's what I'll be doing. Okay, so I will rewrite the complex number by further expanding. I'll use my laws of indices and say this is times e raised to I pi by 4. So let me now focus only on what is inside the bracket, and then we will take the real part. So 4 e raised to ix plus 3 e raised to ix times e raised to I pi by 4. If I take e raised to ix common, I'll get 4 plus 3 times e I pi by 4. Now you can do this addition on GDC. Why did I have to write all this? So that you are basically explaining to the examiner what is that you are putting in the calculator. That's the reason you had to write these steps. So what are my steps? I'm first finding out f of x is 4 cos x. Right? It was 4 cos x, and therefore I rewrote the trig function as an exponent. Similarly, g of x was 3 times cos of x plus pi by 4. I also rewrote that as an exponent. And because they were only cos, I am taking only the real part. Then I said f of x plus g of x means simply adding these two complex numbers and taking the real part. Now I am only focusing on the addition aspect. So I've taken e raised to ix common, and on your GDC you have an option for entering this entire number as it is in the Euler form, which will give you e raised to ix. This should give you a number like 6.48. Again, you can decide to finally get it in the exponent form. You can write this in the Cartesian form, add it, then do it, whatever you want to do. Okay, for example, on your GDC, what it is going to do is, it is going to take us 4 plus 3 times cos of pi by 4 plus I sin pi by 4. 4 plus 3 cos pi by 4 are all real parts, so they'll combine this together, plus I sin pi by 4. The sin pi by 4 is 1 upon root 2, so it's 4 plus 3 upon root 2 is the real part, plus I 1 upon root 2 is the imaginary part. So this new complex number will have a new modulus and a new angle. That's what we are finding out. So your calculator is going to find that out for you and get it in the form that you want. You want it in the Euler's form, you want it in the polar form, whichever form you want. It will get it, and you can further write it as e point. So this is the answer that I am getting when I do it on the calculator. So what is my number, final number? My final addition is e raised to ix times e raised to 0.334i times 6.48. 6.48 is like the modulus. And what did I have to do? I had to take only the real part of this number. Okay, so first let me rewrite the final number. It is 6.48 e raised to I x plus 0.334. What is the real part of this? Real part is only the cos term. So 6.48 cos of x plus 0.334. That is the final answer of fx plus gx. It has the same, see, I just showed you graphically. The magnitude changes, the amplitude or the changes. The frequency remains the same. There is now a different phase with respect to the original function. That is how we use complex numbers for adding sinusoids.